Thank you very much, Rena Madam. Uh, this was really a nice gesture from your side that you have narrated so many things about me, um, and your kind words are really very well taken. Thank you all. These technologies are new to us, those who are at senior positions and those who not have studied during their undergraduate or postgraduate courses while doing, because these were very new even in PG courses. But nowadays, this GPS and GPS have gone trickle down to this secondary school level, and remote sensing even being taught in the UG, and some portion is being taken up in the 11th and 12th standard also. So the technology really penetrating, but for us, since we haven't studied during that time period, still we call it as new. But those who are young and having service experience of 3-4 years, for them it is a usual technology. Now this particular slide is Mashelkar, R.A. Mashelkar's one research paper about the exponential technology he published 2 years back in this journal, and he has mentioned that India need like these 10 big changes in on different technology. So just I have taken two parts of this paper and displaying on this slide. The reason behind is that in even in civil engineering, where we studying, the 4 out of these 10 technologies are directly connected to our construction technology and management kind of thing. Like internet and sensors are in automation industry, we are using one, and fifth, artificial intelligence and the big data on ninth number. We analyze these data in terms of the kind of consideration for management of natural resources, and also the force analysis in many times in like dams and reservoirs. We use these data and analysis of big data in terms of these two. We use these two technologies. So if we say that civil engineering is not connected to these emerging trends in technology, then this is not that we are not accepting the truth of present age, and we need to understand each and everything out of these 4 technologies. What we are studying today has been introduced since last 10 years in the university syllabus, but yet our students are not comfortable in selecting electives based on these technologies and connecting to the civil engineering problems. So my request through this slide is that we should make ourselves comfortable first, and then we could make our students comfortable on the technology front. If we do not embrace all these technology, then how could the students going to be? The title carries remote sensing and GPS, but GPS, when we say, then it is a kind of proprietary product of the United States. It should be like Global Navigational Satellite System, GNSS, which you might heard many times that it's a GNSS, and in the many subjects this term being repeated. But GPS has become very synonym to GNSS, and while discussing all through like GNSS, we keep calling it as GPS, that we are discussing different components of GPS. So whenever I even call the GPS, then you understand that we are considering and discussing different components and different aspects of GNSS, Global Navigation Satellite System. Now, the slide which carries the graticules, why we need the global satellite system, navigational system. That is the main purpose was military in the during the Second World War. That when they are firing missiles or targeting certain points, then exact pinpointed target hitting was not there, and it is going off. and they need a kind of uh, uh, direct hit onto the target. So what could be like the development uh, in terms of navigation system on not only for person from one point to another, but also for the arms and ammunition which are being carried by the carriers. So that is what it is, and now we want that it was required that time that it should be like a system of graticules which cover the whole globe in terms of. So here a spherical bowl is shown, and it is covered with like parallels and meridians, and you know that we call it as graticule to understand the latitude, longitude, uh, uh, points of any location onto the surface of Earth. So this is one of the another representation that why we need the exact location. If we do not have exact location, then difficult for us to really carry out the technological aspect of any phenomena, or in terms of war, that the target hitting is not possible. So here a symbolic representation is given to you in terms of a sphere, and from the center of that, the terms, the latitude, longitude, and altitude are being measured. Now, the problem lies here that where that center point is, whether this one here or somewhere at 10-15 kilometers left or right of it or above it. So that was a big trouble. For that, what is needed that uh, the exact pinpointing of this or the shape of the earth need to be defined, and then it need to be projected onto the paper. So while projecting the earth surface onto paper, what we require that we parallels and meridians we have to bring them down onto two-dimensional piece of paper, and if we are bringing them, then we can unfold the earth in this format. So you could have a kind of visual like this while unfolding the earth, and we could look at different points including our country on this and different other countries and oceans onto the piece of paper. Here, from the center meridian, prime meridian, 0, 180 onto the east and 180 onto the west. So negative marking is done. And from the equator, it's up to the pole, north pole and south pole, 90 and 90 both sides. And what we get is called a graticule. And all these are measured in terms of degrees and minutes and then seconds we are familiar with. The expanse of Indian territory is shown here onto this sketch, that where it goes like 72 to 92 in terms of latitude, and in terms of longitude, and latitude is about 8 onto here, and 36 going up there. So marking is done 8 degrees and 4 minutes to 37 and 6 minutes and 68 to 97, and in is 3,000 kilometers from north to south, and from the eastmost point to the westmost point, if we draw a line like this. This is because this is required in terms of while developing the IRNSS system, like system. So that is what the coverage of whole territorial area is to be seen in this. Uh, we have seen just the spherical graticule system and unfolding of earth, and then measurement. So for standards to be maintained throughout, like in physics, we have understood that for MKS system, meter is the standard. Likewise, in terms of, say, the navigational system and geodetic system, what we need, that we need a reference point. In surveying, we call it that mean sea level is at Bombay, or earlier it was Karachi or like that. So here we need a datum datum from where we could take all three x, comma y, comma z, all 3 points, or latitude, longitude, and altitude. So for that, we need to know the geometry of the globe or the earth, that how it is and how it looks, and which shape, if we assume or adopt, then it perfectly produce the result in terms of x, comma y, comma z. So this WGS 84, 1984 World Geodetic System has been created as datum and coordinate system, to pinpoint a particular location onto the graticule or onto the map, so that that can be perfectly or precisely marked with a lat long. And if we are using it, then it represents reality. It represents reality. It's like within few centimeters, we can say the object or target could be from what we have taken the measurement in terms of GPS output. So the datum, basically here there are three things. One is datum, second is coordinate, and third is projection. In GPS or in GIS also, we use these all three things. So datum, basically from where it originates, like in datum surveying we take the MSL, so that kind of thing. And coordinates, then taking distances from that datum, say origin point. In terms of Cartesian coordinates, we fix our origin at one, say, bottom left corner sometimes, and sometimes in the middle of the graph paper. Likewise here it is the center of Earth. So defining the center of Earth is difficult. So in the next slide, I will show you that how this been taken up, but this is how it is. But there are many other datums, but this is used in GPS. That this datum and this coordinate system has been used in GPS, and this is also basis of the geodetic surveying. So we teach mostly the plane surveying, two-dimensional surveying, in which we do not consider the curvature of the Earth. But if we consider that curvature part, then geodatic, the datum should be taken as WGS 84. The projection systems here mentioned at the bottom of this writing is the UTM, state plane, and polyconic for India. Projections are those who are new, those who are not aware about the GPS and GIS and GIS and remote sensing. The projection system, that different maps created, different layers created, are in different projections. Some data we download it from the US and they are in UTM or state plane projection system. But in India, most of the maps layers are created in polyconic. So this depends upon that which part of the earth we are lying, and while unfolding, what we are compromising. Sometimes we are compromising the linear dimension, sometimes we are compromising the area, and sometimes the volumetric, because this round shaped earth or the spherical earth need to be brought onto the paper two-dimensional. So there are going to be distortion in length, area, or volume. So that particular, whether we are on equatorial part of the globe or towards the polar regions of the globe. So depending upon that, and primary purpose of creating a map, decide that which projection we are taking up. So mostly in India we are using polyconic. This is how we decide the WGS 84, the origin point, say 0, 0, 0, x, y, z, or let, long, alt. So that kind of thing is to be here. And this is a geoid. It's not in this WGS 84, the Earth is assumed to be a geoid. Geo means Earth, and ID. Geo's ID, Earth's ID. So geoid is the term coined after the geo ID is given, and Earth is assumed in this particular shape, wherein the two different radii is taken, A and B, whose values are different, and if we draw a sphere by assuming a formula like 2a plus b by 3, then what we get is considered as a average radius of the sphere, which could be represented, or which could represent the Earth. So that is 6371, and that originates from this center which is being if we put on to the center of the geoid here. So this is how the origin is taken. Now this is the basis of the technology. If we do not understand these things, datum, coordinate, and projections, then we cannot understand the geographical technologies like remote sensing, GIS, or GPS. Today, I'm going talking mostly on GPS, but at the same time, I'm also would be comparing this part of remote sensing, which are going parallel to GPS. That part fall into the signal domain of the GPS. While discussing signals, I'll discuss some part of remote sensing, that how we could compare these two technologies together. So here the GPS is basically three domains which we have seen since long in all books. These are covered: the satellite, the signals, then satellite, the control, and then receiver data processing or instrument, which is there on our hand while doing or taking the coordinate of any location. So this diagram shows you that globe is covered with many satellites, and in GPS there are certain 29 active satellites. They have launched more than 50 satellites till date. The US government has launched more than 50 NavStar satellite. But actively there are 29. What they need is 24. Rest of the satellites are like stepney in our scooter, and they are kept ready in case of any eventuality or failure of the some. The launch of these satellites were done in Block 1, Block 2, Block 3, Block 4, and so on. And they were not launched at a time like in IRNSS. We have done yet the 7 or 8 satellites only, not all the 24 satellites required to cover the whole space which can cover the whole globe at a time while tracking through GPS. So what is basic technology? Now, after studying that how to locate the x, y, z, x comma y comma z, that the location, how it work. So this in picture, a globe is probably visible to you here, to you, and this is written x comma y comma z comma t also at a particular time. The location, because this time is important when we mark, then different satellite system, different satellite numbers are present to bisect this point and give us the exact location. So a particular timing is also mentioned along with the coordinates. So that is what is the thing here in working of the GPS. What is here? The points are important. So I'm going to give you a kind of understanding here based on the principle of trilateration. This is the working of GPS is basically on the principle of trilateration. This is a geometrical principle. There is no formula used here. So many times we get confused with that. Where is the method? So basically, this is a geometric method through which we calculate. Though we need the calculation of the speed, distance, and time. Definitely, they are involved in calculation of trilateration. But basic fundamental about this principle is the geometry through which we receive the signals and we draw the circles from those signals. So calculate time taken from signal to travel from non-satellite position to the receiver. This is important here. Here in this, the satellite is emitting the signals, not the object. In terms of like remote sensing, what we do, there is a source of energy or a signal, you could say, and it is emitting energy, then getting reflected from the object, and then being caught by the receivers or sensors in the remote sensing. But here, receiver are directly receiving the energy from the satellites which are hovering in different orbital planes over the whole globe. So that is what the thing here. So this The third is the distance from 4 or more satellite is calculated. 4 or more at least. This is why this is because this is based on principle of trilateration, and that is for three-dimensional calculation. So anything? There is noise, a question or something. If then you could ask, otherwise I will continue. Okay. So distance from 4 or more satellites is calculated. Means what? We need signals from 4 or more. Why? Uh, I request if there is no question, please put off or switch off your mic. All participants. Uh, Receiver calculate its position. Now calculations are done in the receiver, maybe handheld or kept somewhere, maybe on board on flight or satellite, which are not the GPS satellite, different satellite which we launch for other purposes like for remote sensing or for meteorological purpose. So those receiver calculate its position on Earth based on interaction of these ranges, distances in geoidal space defined by WGS 84 frame. So let's go ahead how it works. So this give you a kind of understanding that if we have three circles in 2D, two dimension, then exactly pinpointedly this one point can be drawn. This one point can be achieved. If we draw two circles like this, they are just touching each other, and third, where it cut, then exactly we'll get it like this. So the third point can be done geometrically if we understand the the thing if there are on 2D. It's not three dimensional. These are circles, not spheres. But when it is sphere, then what is it that one measure one signal from one satellite measurement narrows down our position to surface of a sphere. This gives that these satellites are like something 20,000 kilometers away from the Earth's surface. The remote sensing satellites are not that far off. They are hardly 500 to 1,000 or 1,200 kilometers off the surface of the Earth. But the GPS satellites, they are far off, like 20 times 20,000 kilometers or 24,000 kilometers. So this is the range they are. So from there, if we are receiving signal and calculating distance, then all the points falling onto this sphere, then all the points could be our position. But if we take one more, if we are taking one more signal into receiver, then the receiver where the intersection of these sphere, then the whole circle, a second measurement narrows down our position to the intersection of these two spheres. So where somewhere the intersection point, this middle portion is where our position is lying. Now the third, if I show you, then the third measurement narrows down our position to just 2 points where the first two here and the third, this calculation is this calculation showing us the intersection of these points are like this. Now these three dimensional, if this is two dimensional, then we'll get only single point. But in three dimensional, this is so fourth one will give us the exact location that this is the location where our point is, whether onto this front side or back side of the sketch of the slide, like these two pink points onto this. So fourth measurement will give us the exact. Now this understanding of 1100, then 1505 miles and 12,000 miles, what it is. Now this is what distance is equal to travel time into speed of the light. Very simple equation is this. So what is calculated by the receiver is the exact time of travel by the signal from the satellite to the receiver, and this is billionth part of the second is accuracy of this time travel signal. Billionth part, I say. The after decimal there are nine digits, and if only there is one single say kind of inaccuracy, it may lead to say 200 300 kilometer away we are targeting a point for hitting through missile. So that kind of accuracy is required here in this. What is important, that measurements are big. We can't imagine this kind of 20,000 kilometer, 22,000 kilometer or something like these distances. This is not possible. You know this this is beyond imagination, but they are taken care of. Speed of the light and travel time and multiplying, we get the dimensions like this. Then we are arriving at a point x comma y comma z. This is not exactly x comma y comma z, but these are lat long and altitude of the point. So this is a trilateration geometric explanation of the kind of signals, and then the locating a point. This you might have seen many a times, this diagram of the various parts of the energy which we propagate through the atmosphere to the receiver, and in terms of say remote sensing from the energy source to the ground features and back to the satellite where our sensors are mounted. So why I'm keeping this here, that very interesting thing is that the working of our remote sensing system mostly takes place in visual range here, 400 to 700 nanometer, or say 0.4 to 0.7 micrometer range here. The bands are used here, and then the near infrared, near infrared and short wave, medium wave, and light infrared ranges. Then there are microwaves and radar, and the next level of energy in the sunlight electromagnetic spectrum is the radio and television waves. The what we receive in our radio, and the waves are lying in this range. So 1 meter, millimeter to 1 meter are the radar, and beyond that you can consider all our radio and television waves. So most of the waves which we receive in GPS are falling onto this area, which we do not use in remote sensing. We do not put this segment into use, and there is lot of attenuation here in terms of remote sensing, but for the sake of receiving directly onto receiver, these waves are comfortable and they are taken care of. I assume you are comfortable with this, and if Utkarsh, anything you want to interrupt with any clarification, if you are not getting, then I'll show you. These are the altitude ranges of different locations, uh, kind of things. The spacecraft, then the supersonic plane, then the commercial aircraft, then the parachute, and balloon, and this kind of boundary. This is Mount Everest. You could look at here the elevation from the Earth's surface. This is sea level mentioned here, and this is a logarithmic graph onto here. And this are also temperature ranges shown here, that how temperature changing, but we are least concerned with the temperature, but you should be concerned with the elevation of different things which are taking place, because while uh, capturing the information, what we require are these that from where and at what distance we are capturing. So this is how I explained the first slide, and then again the slide is. Now I have explained to you the importance of knowing the time, that how the almanac here, the term almanac used is the kind signals receiver receive from the satellite. But satellite is not sending only the signal, it's a value or something. It also send many other information about the satellite and the atmosphere, orbital information. So altogether that is considered as almanac, sent as part of satellite message, tells the receiver exactly where each satellite is located in its orbit at a given time. So what is important, because we draw a circle, a sphere around the satellite, not around the globe, and the bisection point give us the location of particular position on Earth's surface. I think this is clear in your mind, that we draw, while trilateration we are using, that we draw a sphere of the distance, time taken into the speed of light, that 3 into 10 raised to the power 8 meter per second, we multiply and we get distance that comes in terms of say 15-20,000 of kilometer. That is the distance between surface of Earth and that. So while receiving almanac, what we also receive, we receive many other things about the satellite which are sending the signal. Receiver acquire and logs into signals from each visible satellite. At least 4 are required, 3 are not sufficient. If 3 are there, then we have to decide which point out of 2 the possible points. So from pseudo random coded signal, these signals are like not exact. Not exact. The word pseudo is used with this all coded signal because almanac is not directly decoded. The receiver calculates when the signal left the satellite, because the satellite, while leaving the signals while leaving the satellite, and by when it arrives at the receiver end or into the receiver. So there are 2 points. Difference in coded signal between time it left the satellite reached the unit is calculated precisely. This is how it is being shown onto the slide. The difference between reaching the signal when it left the satellite and received by the receiver onto the ground surface. So if this much is the difference of time, then this need to be taken care of while using the method, geometric method of trilateration, that we should give consideration to this. This was something about the uh, uh, what we understood till point is only the science or something, how it works, how GPS or GNSS works. But let's see that why and how it is getting developed in and around the countries of world. So this is the development of GPS, which I was talking, that the need established during the World War II, that pinpointed location, especially by military purposes, and then after into the civilian uses this has been put. So GNSS concept design in 60s, engineered and built in 70s, 80s, first satellite in orbit 1970. This is about GPS only, not any other uh, country. So 78 first satellite launched and 90 positioning available. The 1995 full operational capacity of GPS. So while I was doing my engineering, GPS was not there. When I started using mobile, GPS was not known to me in earlier days, early 21st century. But it became so certain that each and every device now carrying a GPS in last 5 to 10 years of time, that even the engineering methods are being redesigned using GPS. like we did everything with the remote sensing earlier, say 40 years, 30 years. Now the similar things are being redone with the GPS. So that is how the penetration of this technology is into the engineering domain, not only in civil, but other engineering like they are also using this technology. So this 1995 is FOC, full operational capacity. Other system we are just going to get a glimpses of GLONASS and Galileo and Compass, so that we are also have a kind of one slide presentation. The constellation of all these systems of GNSS is continuously changing because of introduction of new satellites and the expiry of the existing satellites, or when some satellite fails, then they keep updated and they keep updating their system with the additional satellites. Now, look at this. The the most of working is similar of other GNSS. This is a Russian navigational system, GLONASS, and like they also have launched and now it's operational. The Russian navigational system, or Russian GPS, you may call it. They call their name to this is GLO, GLONASS. Likewise, the like the Russian and the US, there is European and Chinese. So there are 24 active satellites. I said that this 24 active satellite is not hard and fast. That depends upon the altitude of the satellite, like 24,000 kilometer above the surface, or 20,000 above the surface, or 30,000 above the surface. So depending upon altitude and orbital characteristics, and this been decided, and the 24 is general number used that they are, but they are not in same plane. They may be put into 3-4 planes. Just hold for a minute. I'll be back in 1 minute. वो एलडी का एक ट्रेनिंग चल रहा है. हाँ. अच्छा, तो आप क्या ऐसे आज घूमने फिरने आ गए क्या? नहीं, वो चेक ट्रेजरी को वो सरकारी मंडली का चेक लेना. हाँ. अच्छा. तो मैंने सोचा कि चलो जाके आते हैं. हाँ. तो हो गया क्या आपका कोऑपरेटिव का काम? हाँ, वो सब हो गया. जेएस भाई से हो गया? हाँ, हो गया. ठीक है. वो चेक वेक ले लिया, मैंने बोला आपसे मिलती रहती हूँ. हाँ, जरूर. वैसे ही चले गए थे. हाँ, उस दिन तो क्या हुआ, छुट्टियों में सब हो गया था, और आपने मेरे ख्याल से छुट्टियों के बाद ज्वाइन किया था वहाँ पे. नहीं, छुट्टियों में ही ज्वाइन कर लिया था पहले. पूजा मैडम तो बाद में आए थे इधर. नहीं, इन लोगों ने ऐसा बोला था. नहीं, पूजा मैडम ने भी तभी ज्वाइन किया था. इन लोगों ने ऐसे बोला कि नहीं अभी ज्वाइन करो. अच्छा, ठीक है, तो कर लेते हैं. अच्छा. ठीक है. एलडी में एक ट्रेनिंग चल रहा है इसका, रिमोट सेंसिंग जीपीएस का. तो एक लेक्चर मेरा शेड्यूल था, तो बस वही कंटिन्यू कर रहा हूँ. ठीक है सर. वो दूसरी सर आपको याद कर रहे थे. ऐसा मैंने वो रोजा को हाँ. We were together. हाँ, ठीक है, मिलते हैं. हाँ जी. Sorry for little. Okay. So what I was explaining you, that all the satellites are not in single plane. They are kept into 3 planes like in GLONASS. They are in 6 planes in GPS. So this differ for each and every system, every country they are using. So initial operational capabilities and FOC, this has been now operational. Russian satellites are operational. Date is not mentioned here, but initially this was done with 1993. But here is something like 2011-12, and it is operational now. This is the European Union. These are global navigational system. All are like this can be used anywhere onto the surface, and they are completely developed, not like restricted. Our IRNSS system is not global; it's a regional system. So you just differentiate that these two terms, that what is global positioning system. GLONASS is also global. GLELU is also a global system like GLONASS and GPS. Now they are also operational with all this, and they have different satellite position, but the methodology and the functionality remains almost similar. This is something also about the Galileo, the kind of European Union GPS or GNSS, 30 satellites, something in 23,000 kilometer above the Earth, and so on. This is Chinese um, satellite system. They call it BTS, but generally in international arena, this is a kind of, they call it compass. They have given name it as a compass system of GPS, but locally they call it as BTS or Baidu navigation system. This is operational there. Fully operational in China, the compass system or Baidu navigation satellite system BTS. This is something about, I won't take much time, I'm just going through so that you could have a kind of comparative understanding of this. The Indian regional navigation satellite system, we have been receiving this news into our WhatsApp messages and on other social media that India has become like one of the now the fourth country, but in terms of only regional, they have recognized, not globally. This system of IRNS, we don't have that many satellites. There are hardly 7, 8 satellites in the space, but the whole territory, geography of India surrounding and 1,500 kilometer beyond our boundary, we could scan each and every point onto the surface. Why 1,500 kilometer? It covers almost all the countries nearing, like not whole of the China, but it crosses almost middle of the China and on to the east of the India map and onto the west, like Afghanistan, Pakistan, and other countries. This satellite covers whole area, and this has been commissioned and it's working perfectly. But it doesn't cover whole globe. This system of 7 satellites, one additional satellite is there, which is as a standby. If something fails above, then they can launch it and replace it. So 7 satellites which are functional, and they are giving the each and every part information of the part of our country, as well as you could imagine that it is beyond the boundaries of this and up to something 1,500 to 2,000 kilometer from our boundaries. The information can be captured. Now, major thing is that India government is propagating it as that all the electronic goods where GPS is getting fitted for the navigational purposes and other purposes, they should put to use the IRNS. So let's see that what would be the development beyond 2020, in 2021, or if there are certain things, then government can make it mandatory. I'm taking you through this quickly, the three segments. Earlier, I have explained only the parts. I haven't gone into detail of these 3 segments of GPS. That satellite, the signals, satellite, the control, the receiver, and data processing, because these are the major things which are being covered in many of the our UG syllabus and PG syllabus. But let's see the detail which are not there in the books available. So you pay please attention towards what is being shown onto the slide, and we could use it to the students of UG as well. The GPS satellite constellation may look like this. If we put 24 satellites around the Earth surface globe like this, then all are like taking rounds around the Earth. The space segment, minimum 24 satellites, some additional standby 7 to 8 altitude, something like this satellite transmit GPS message needed for, like satellite transmit here, the GPS message needed for positioning. We need many signals to get the best position information. More than 4. If we have more than 4, we could improve our location accuracy. Like in DGPS, one is more system of GPS is DGPS, and in that we also use some signals from the ground stations, and we could improve the accuracy to some centimeters only, to 5 centimeter or 3 centimeter, with that much accuracy. These are some of the kind of satellite, how the satellite works and the things which are there. 2 solar panels for power. Main body is the size of a small car. 2 to 4 atomic clocks for measurement. I say billionth part of the second is measured by these clocks. So atomic clocks are used here. Each satellite has a unique SV number. This is about GPS, and the block there have been launched in like block 1, block 2, block 3. These are the orbit 6 different planes, which minimum 4 satellite in each, and the height of the orbit is 20,000, 12-hour orbit. You should keep those things in memory, that these are the important things, something. Now the second is the satellite signals which they send is, there are 2 types of, like in, while we study the physics, that signals are carried by the carriers. Even in the mobile technology, the carriers and carriers are used to carry the weak signal, the signal which are not strong. So carriers, they do not carriers are helpful in maintaining the quality of signal. So L1 carrier and L2 carrier. L2 carrier is for military only, while L1 carrier here is for military and civilian purposes. The type of signal which are being used for civilian is CA code kind of signals, while the for military purposes, which kind of the P code signals. So why these names are given? These are just like in remote sensing, we have like single band monochromatic remote sensing, then multi band remote sensing, then hyper band remote sensing, hyper spectral remote sensing. When there are hundreds of bands involved in for doing the remote sensing, we call it hyper spectral remote sensing. Likewise here, a particular band is used, particular signal is used for the purpose of getting the position of a point. So P code signals are for military, and ACA code for civilian, and this is also used for the L1 for navigation messages. L2 type of carrier, this is megahertz mentioned here. You could see the radio waves 98.3, like 91 radio हम सुनते हैं नहीं सुनते हैं, तो वो वाला ही उसी रेंज में ये सिग्नल्स हैं. इनकी जो कैरियर की फ्रीक्वेंसीज हैं, द रेंज इज नॉट बियॉन्ड, दिस इज 1227.6 and 1575.42 मेगाहर्ट्ज. तो ये हम रेडियो सिग्नल्स है, बेसिकली रेडियो सिग्नल्स एल बैंड 390 to 1550 मेगाहर्ट्ज तक है ये सिग्नल. एंड L1 कैरियर ये है, L2 कैरियर ये है, ये इनके सिग्नल्स हैं, और एडिशनल civilian with S12 for aircraft. So this is how the kind of satellite signals are being propagated through the atmosphere, received by the receiver on Earth's surface. Maybe handheld in position, or maybe in kind of जो हमारी नेवी की पनडुब्बियां हैं उनमें लगा होता है, या एयरफोर्स के जो एयरक्राफ्ट है उनमें लगा हुआ होता है. तो ये जो किसी भी वॉरशिप्स में लगा हुआ होता है, तो किसी भी चीज में जब लगा हुआ होता है तो वो रिसीव करते हैं इन सिग्नल्स को. इवन हमारा मोबाइल है, तो मोबाइल हमारा ये जो सिविलियन CA कोड सिग्नल्स रिसीव कर रहा होगा। Here, one thing is mentioned that L1 and L2 wavelength of this 190 mm and 244. This you could compare with your remote sensing knowledge that the 1 mm to the 1 meter ranges for the microwave. So that is what is the bandwidth of the remote sensing, microwave remote sensing. Here, these wavelengths are almost overlapping where the radio signal starts and the TV signals start. So that is what the thing is, and other are just physical properties. Somebody putting up research work, then definitely go into detail of this. Otherwise, the information is quite sufficient, and um, this needs to be just digested, and not I won't recommend going detail into for UG process. Even this is just for the pictorial representation, how the signal is being taken, CA to P code, and then mixing of signals, and these mixers and modulations even done. And these signals are modulated while before receiving into the receiver. So this slide is only for the purpose of that what happens to the signal. Signals are not directly taken by the receiver, but it's processed and further processed, and more processing is done to arrive at positions. So it's a lot of processing at this part. So this slide is just that the high frequency, there is a pictorial representation of high frequency and low frequency, that these signals are being taken by the carrier of high frequencies. So that is what is the understanding. Now we have understood the one part, the signal part or the satellite part or space segment of the uh, GPS. The second is to control these all what is happening around. There are 4 monitor stations located by GPS. This is all not about Galileo or compass or anything else. This is about GPS. Say what they have. They have world over their control segments. They may allow you to use GPS. They may not allow you to GPS. So how these are being taken? That 4 monitor stations located around the world: Hawaii, then the Diego in Indian Ocean, then the uh, Ascension Island in the Atlantic, and then Colorado in the Colorado. So these 4 stations are there. They control the whole geography of this globe, and they may open up certain areas. They may close. They may say that India can't receive their services. May stop someday. So why? What is the need of creating of IRNSS by spending say thousands of crore rupees by the Indian government? That this is not reliable. One thing. Second thing, that they may allow us to use, may not allow us to use. They are allowing us as far as their business strategies are working. So they giving us the access into using the GPS. But the one day, fine day, if they are not having good ties or they say we are at warheads, then what will happen? So they may cut. So there are control systems they are having in all 4 the critical locations all over the world. They are having this kind of. This is a major 4 monitor stations located like. So I'll show you. And this is monitor stations. Then master control stations are there, like these 2. uh, and then 4 large ground antenna stations that broadcast signals to the satellites. So let's see this image, that how the things are happening around. This technology seems very small, but large implications on the technology development and other which are dependent on this technology. The dependence, like we are creating a survey system based on GPS, so that is not possible. You can't rely for say next 10 years or 20 years based on GPS. GPS may be available or may not be available. So what to use is that we should have our indigenous IRNSS, and we should put embed that into our development of like remote sensing system. We are having many satellites in the space, and likewise IRNSS has been developed, and now you might be getting that why control they are doing this, but we can't avoid it, we can't eliminate it. Eliminating it like China eliminating the world business and other things, which they are really creating curtains all over. So that is a kind of different situation. But this look at here, that how this things is happening. I'll show you one more picture which will give more understanding the things being controlled. The satellite here, this PCA code which we L1 L2 carrier, remote monitor stations here, then ground stations send the orbital information to the master station, then ephemeris means something like orbital data, clock data, control parameters, the ground antenna, then S-band data back to this, and what this is emitting signals its position and going down. What is happening? It giving its position, and based on this distance covered multiplied by the time taken, a sphere is created around the satellite, and then we use the 4 satellite data, and then we fix. So this is receiver here mentioned in the center. A is the point whose coordinates we are interested in. So how this is the operational control taking place is like this. Now GPS master control and monitor network in and around the different countries and oceans is like this. What we have seen earlier, like 4 plus something like this, 4 here monitor stations, then there are master control, then there are ground antenna. All are and those things are marked onto the map, world map here. So you could look at this Indian Ocean, they are having here the monitor station. Then in this Pacific Ocean, you look at Hawaii here, and then Atlantic Oceans also they are having here, and other countries they have access like this international terrestrial reference frame. They have a kind of reference frame, they can on off the access to this technology by switching on and off, like we do to the lighting in our room, that we can on off thing can happen with this kind of through this kind of frame, reference frame. This is very understood. We know each and everything of it. We might, you might have seen it lying in survey lab of the department, that GPS receiver is like this. आपके जो मोबाइल है उसमें भी इसका है, और कुछ गाड़ियों में भी फिटेड दिखेगा आपको जीपीएस ट्रैकिंग और नेविगेशन सिस्टम भी दिखेगा. तो जो नई नई व्हीकल्स हैं उनमें ये सारा फैसिलिटीज धीरे धीरे एम्बेडेड ही मिल रहा है. I'm not going to go detail into user segment. This is something important in user segment, that what is required for civilian use and for military use. The receiver, what it does, that two things are there. The standard positioning system and precise positioning system. That standard positioning system we need for civilian, that is not that much, but for military it's very precise. So again, depending upon the signals it is sending and the clocks we are using. So based on, for civilian SPSS positioning, this is used for this relies on CA code and L1 signal. Selective availability can be used to degrade signal. Then for military use relies on P code, L1 and signals, and P code on 2 frequency increases accuracy. I'll take 5 more minutes only for the application of this part, and then we'll switch over. I'm switching over. I'm not going to, because receiver part is very much comfortable. We are all not going to detail. These are different components. This is precision timing, where importance is shown here to you about that error of 1,000 of a second. Positional error of how much? 300 kilometer. Error of 1,000 part of a second may lead to 300 kilometer of positional inaccuracy. So that is what is why the atomic clocks are used here. Now these are final concluding slides from my side, and then we'll speak to you. You could also have some other uses of GPS rather than this. Location, determining a current position, navigation, determining distance and direction to a position, then data logging, recording characteristic about a position, because altitude is used, surveying, data logging, the third component, the altitude is used for like leveling we do in surveying, also done for point positions. The surveying is easy with this GPS. So location and location, basically if all three are covered with precision, then it is more precise than even these total stations, and those things can be done. Furthermore, even if it is not precise, then what is that the total station surveying is not possible in many other areas where GPS is done, like in the enemy territory, like or the territory which is where the total station cannot be taken onto the islands and other area which is in deep mountain regions and other areas. So GPS is really some way out for that. This is also used for timing कि कभी फायर ब्रेकआउट हुई है किसी जंगल में, तो GPS can be used for that timing also. Geodetic survey, transportation, large construction, so many things which we could apply into the engineering domain. Some other uses are also mentioned here.
Thank you very much, sir.
Okay. Okay, thank you all.